Okay, my name is Benjamin Deniston. I'm with Mr. LaRouche's scientific research team, his what we've called the basement research team. And I'm going to give a kind of somewhat brief introduction and discussion of a new program, a new challenge that Mr. LaRouche has put on the table, that Lyndon LaRouche has put on the table regarding really the future of mankind on this planet and in the solar system, which is the challenge he's laid out regarding the development of an advanced fusion economy using a special fusion fuel on the moon, which we can find on the moon, but we can hardly at all find on the Earth, and the development of a lunar perspective to drive the development of the world economy and the recovery of the global economy. So this is a rather exciting and somewhat shocking perspective to a lot of people. I wanted to just open up by emphasizing some of the context and the background, and then discuss a little bit of the implications, and then leave plenty of time for questions and discussion and thoughts from the people on the video call here. So I think, as many people are very aware, we're in an incredibly dramatic situation, and Mr. LaRouche has put this conception of this Helium-3 lunar fusion program on the table in the middle of a very dramatic shifting situation in the world. And what he's highlighted and what he's picked up on is specifically China's role, the role of China in repeatedly stating and pushing and popularizing and presenting their intentions to do this, to go to the moon, to develop the Helium-3 resources from the moon, and to utilize these Helium-3 resources for the development of an advanced fusion economy back on Earth. And what this is in the context of is China's role, along with other nations, Russia, India, and other nations, in completely breaking with the existing global monetary system and leading the world in a whole new direction of advanced scientific development. And there's a long history to this, a lot of elements to this, but I think it's worth referencing what China did in 2009 when they threatened to walk out of the Global Climate Change Summit, the Copenhagen Summit in 2009, where China led the resistance to the British attempt to impose a binding carbon emission scheme upon the world to limit development through this whole climate change fraud, through this Copenhagen Summit in 2009. And China led the resistance to that and said, no, we're not going to go along with this. We'll walk out of the convention in protest, leave the convention if you insist on trying to impose this ban, this binding cap on carbon emissions. And it was enough to get the British Queen herself to state publicly before the entire Commonwealth, leaders of the entire Commonwealth, explicitly stating that the #1 goal and obligation of the British Commonwealth is to push this zero growth, population reduction, climate change fraud. So it really drew out in clear terms what the dividing line in the world situation has been and was then in 2009. But I think it's a useful reference point to look at what's happened since then. And the most recent dramatic developments around the BRICS summit in South America, with the nations, again, of China in collaboration with Russia, Brazil, South Africa, India, stating their intention that they're going to go with this development perspective, announcing to create a new development bank for the construction of infrastructure, scientific advanced technology. They're going to just develop their own mechanisms to facilitate a whole new level of investment and development and growth, which was being denied to them under the current system. So, and in line with that, we've seen, I mean, we could spend a couple hours going through the number of bilateral agreements between various nations to develop high-speed rail, new agriculture, new agreements on space cooperation, new agreements on nuclear power, just a whole array of very exciting developments showing the world is shifting away from this zero growth paradigm which has dominated for so long. And there is a serious force on the planet emerging, centering around China, Russia, India, and an array of associated nations that's saying, no, we're done with this. We're going to go in a new direction. We're going to go in a development direction. And we're going to create our own system if we have to do that. So now, in that context, I thought it's worth reflecting upon that Mr. LaRouche, in examining all these breaking developments, the shifting global situation, he has emphatically pointed to the importance of what China stated in their intention to go to the moon, to their intention and their desire to develop the moon, and their intention and their desire to develop the moon for this advanced fusion fuel Helium-3 and bring that back to Earth as a power source for the creation of an advanced fusion economy. That this has been what Mr. LaRouche has identified as at a certain point he called it the metric of any sane, any competent national economy right now. He's called it the benchmark or the guiding post of the entire global reorientation right now is what China is doing with this program. So in the context of all these very exciting developments, all the activity going on, Mr. LaRouche has pinpointed this particular mission and this particular objective to develop an Earth-Moon fusion economy, so to speak, as the most important driving point or defining point which we need to focus on, which then determines all the steps back from there. That this is going to be the program, because there is such an abundance of this fusion fuel on the moon, and because it expresses, I'll get into a little bit, a higher quality of fusion fuel, which enables you to have a higher quality of energy production and energy capabilities for your economies. That this will provide the biggest boost, the biggest gain to a suffering world. This will provide the biggest leap in economic productivity, in value creation, in progress, in real physical economic growth, which will enable the development of the entire global economy up to the required standards to sustain not just the current population at a decent living standard by today's standards, but will sustain the reaching of that point and the progress beyond that in really unleashing the capability for the development of the human species. That's really what this represents. So, again, there's going to be a lot of time for questions on the general points, the conceptual points, the specific points, but I just wanted to highlight, and we've covered this on the LaRouche PAC website. We discussed it a little bit in a live webcast with Mr. LaRouche last Friday. But just so people are clear, fusion, there are different types of fusion reactions. Fusion itself is by our current at our current level of understanding and our current access to different energy sources and different methods of different levels of what Mr. LaRouche would call energy flux density. Fusion expresses the highest level kind of within grasp that's achievable. You can conceive of higher levels with matter-antimatter reactions, for example, and that's something that we're going to want to continue to look into and pursue. But in the immediate period right now, what is going to enable mankind's progress is fusion. And the work being done on so-called first-generation fusion systems or first-generation fusion fuels is very important. It's very useful, but it's only a first step, and it's only going to get us so far. And what we want to push for is what we could define as a second generation or advanced fusion fuels, which is what you can get from the moon with Helium-3, a particular type of helium, which is relatively absent on Earth. And again, this was discussed on the Friday webcast in some slight detail, but just to remind people and to put it back on the table, the first generation fusion fuels, when you fuse, you're dealing with two types of hydrogen. And when you fuse those two types of hydrogen together, you bring them together, you're performing actual alchemy, in a sense. You're creating a new element. Mankind's creating a helium element, a different element on the periodic table than the initial fuels, than the initial components that came together to fuse, and releasing a tremendous amount of energy in that process. You know, fusion reactions are literally millions of times more powerful than any form of chemical reaction. Anything, wood, coal, natural gas, literally it takes millions of times more of any chemical fuel to match the energy of a nuclear reaction or a fusion reaction. And many of the methods by which we will be able to get controlled fusion reactions to power the entire world, to provide more than enough power to satisfy all the needs of the human population, including satisfying many of our resource needs. The ability to do that with fusion, many of the methods depend upon creating an incredibly hot plasma and using magnetic fields to contain and control this very hot plasma, such that you're getting the fuel in that plasma to run into each other and fuse and release this energy. Now the problem is that with first generation fuels, with hydrogen fuels, specifically deuterium and tritium, which are two types of hydrogen, two isotopes of hydrogen, most of the energy released in the fusion reaction of those two types of hydrogen is released in a neutron, which is a particle which has no charge. It is not affected by magnetic fields or electrical fields. Plasma is, and any particle with a charge is affected by magnetic fields, which is why you're able to contain this incredibly hot plasma in these fusion devices. But then when the fusion occurs, you get this neutron, which doesn't care about magnetic fields. It's not going to listen to them. It's not going to obey them. It's not going to do what the magnetic fields would ask it to do. And it just flies right out of the plasma. And that is 80% of the energy from fusion reactions is released in this neutron. So to be able to, so one, that creates a lot of problems because it does a lot of damage to your reactor. It makes the whole system a little bit harder to handle because you have to be able to deal with these very high energy neutrons. But it also means that to convert that energy of your fusion reaction into electricity, into power, or to utilize it in some meaningful way. I mean, there's certain ways you can use neutrons. We could get into that in the discussion. We're going to want to use neutrons for certain things. But as a core component of an advanced fusion economy, we're going to have to generate a lot of power, a lot of electricity. And with these neutrons, what you have to do is utilize them to basically heat water, create steam, and spin a turbine to generate electricity, which you can do. It can be done. The whole system ends up becoming more complex and less efficient because of this neutron issue you're dealing with. But it's going to be part of the process. It's going to be something we're going to deal with, and it's going to be part of the development of fusion technologies. But if we really want to seriously enter the fusion domain, we want to have fusion reactions where all of the products created, everything created by the fusion reaction, is for the most part charged particles, meaning they remain in the plasma. They're maintained by the magnetic fields, by the electrical fields in the plasma, which will enable the energy created by the fusion reactions to be controlled and contained in the process itself. And there's a lot that can be said, but the point is this opens up entire new what I would call 21st century methods of power generation, electricity generation, other things you can do by controlling these very high temperature plasmas and utilizing the capabilities and the properties of these very high temperature plasmas. To generate electricity and power, you can utilize various forms of what's called direct conversion. So instead of generating electricity by boiling water to create steam, to run the steam through some pipes to spin a turbine to generate electricity, you can actually, in various methods, generate the electricity directly from the plasma process itself in the reactor. And you can actually get up to twice as much electricity from this direct conversion process versus the standard steam turbine cycle. So already it's twice as efficient. You get twice the conversion efficiency, so to speak. But you're also, more broadly, what you're actually doing is you're entering a domain where you're utilizing the properties and the capabilities of the plasma itself, the controlled high temperature plasma itself, and the energy reactions from that plasma more directly, instead of going to earlier, older methods of just going to a heat cycle. You're dealing more directly with the quality of the energy of the fusion process itself. So the point is, this is kind of a quick sketch on a few things, but this has been, I mean, we're not the first to recognize this. The Chinese were not the first to recognize this. This has been recognized for many decades, that an advanced fusion economy with more efficient, more streamlined, more capable fusion plants, which can provide all the power the entire planet needs for electricity, for resources, for the creation of new types of resources to satisfy the needs of mankind, you're going to want to go to a second generation or advanced fusion system. And so it's been known for some time that this is where we want to go. We might take some steps along the way, but ultimately this is where we want to get to. And so what Mr. LaRouche has done, he's said, well, that's where we should set the benchmark. We should start with that as the objective. We might not be able to say exactly right now today precisely how long it will take to get there, but we need to set that as the defining metric for where we want to get to, and then work back from there. Now, as I said, the main difficulty in this is the fact that the fuel for this advanced fusion reactions, the fuel that has the lowest temperature requirement to get the fusion reaction, because when you're dealing with fusion, you require very, very high temperatures to get the fusion reactions to occur. The fuel that does this at the lowest temperature is Helium-3, a type of helium. And unfortunately, this doesn't really exist on the Earth in any great quantities. You can find a little bit, very little bit coming out of the Earth in natural gas. We create very small amounts are produced in the process of maintaining our nuclear warheads. So we have enough on Earth just to kind of play with in some experiments. But the entire surface of the moon is coated with this stuff, is just embedded throughout the surface of the moon, because it's constantly being created by the sun and blown out by the sun in what's called the solar wind, and it's been constant, and it doesn't reach the Earth because the Earth has a magnetic field which blocks it from ever reaching the Earth. But the moon's just sitting there naked, and it's getting blasted with this stuff for billions of years now. So that the soil on the moon has been just embedded with this particular type of helium, just sitting there waiting to be accessed. And it's been estimated that there's enough Helium-3 on the moon to power the Earth for 10,000 years. Now, one thing we want to do is do some kind of additional calculations on that, because I believe that estimate is based upon current or some moderate increase of power use for the whole world, and then how long could you sustain that with the amount of Helium-3 on the moon. To do a more accurate estimate, we would certainly want to take into account the fact that we're going to be using power at a greater and greater rate as society develops. As society continues to grow, we're going to find we can do more creating our own resources, managing the planet, solving the needs of mankind by increasing the power use per capita, or the energy flux density. And so we're going to be, as we have throughout all of human history, we're going to be continuing to use more power. So perhaps it might be enough to last 1,000 years, or or 2,000 years, or 500 years. But whatever that is, I mean, it's a number that's almost meaningless. If you think back 500 years, where was humanity 500 years ago? How far have we come in 500 years? 500 years ago, you could not have forecasted the details of the type of technologies and developments that mankind has today. Where can we be in 500 years? Where will we be in 500 years or 1,000 years under a lunar Helium-3 advanced fusion driver program? We're collaborating with other nations in the development of the Earth, the development of the Moon, the development of space exploration, all powered by advanced fusion power. You know, less than 100 years, we could be on to completely new power sources that can take us to completely new levels. So the point is, the Moon is loaded with plenty of this resource that is more than enough to take mankind out of the misery of its current conditions and take mankind into a completely new era, a completely new domain, from which, you know, I don't know, we're in a position to forecast what's going to come after that. But this is the enabling fuel, the enabling step to facilitate the creation of an entirely new stage in human history. And that is literally the what we have before us right now. That is happening. You know, Mr. LaRouche said China is doing that. That's what China's doing. That's what you're seeing the world orienting towards. In the United States, we've done nothing for decades. It took us, I believe, 60 years to go from the first airplane to landing men on the moon. And at the current rate of activity, 60 years after we landed men on the moon, we're still not going to have returned to the moon. Since the death of Kennedy, we've been sitting there stagnating, doing absolutely nothing. And right now, we're seeing an incredible process where that entire system that we had adhered to for decades, the zero growth system, is crumbling before us. And you're seeing the emergence of the majority of the world population strongly and actively saying, screw this thing, we're not going to play your games anymore, and we're going to develop our population, we're going to grow, and we're going to move towards the future. And that's what's happening right now. And so the challenge that we have before us is to, one, ensure that that happens, and two, ensure the United States participates in that. Because an alliance that Mr. LaRouche is pushing, has proposed, has been putting on the table, an alliance between the United States, China, Russia, and India, and many other nations, I'm sure, coming along as part of the process. But if you take those four great global powers and you say we're going to cooperate on this objective of developing the moon, of developing bases on the moon, mining operations on the moon, infrastructure in space to have continuous exchange of material back and forth between the Earth and the moon, bringing people there, people back, bringing Helium-3 back from the moon, bringing resources to the moon to develop the moon, all guided under a driver program for advanced fusion power. We're literally talking about potentially the greatest step that mankind has ever taken, the greatest revolution in what mankind can do on this planet and beyond. So that's what we're fighting for right now, and that's what we see before us right now. That's what we have. That's what humanity at this stage essentially has in its grasp that we need to fight to create. So that's kind of just a brief general introduction, and I had spoken with Diane earlier, and we had said we'd agreed to keep the opening remarks a little bit short and condensed, just kind of touching on a few things here and there, to ensure that we have plenty of time for more discussion and dialogue on this whole perspective, on the details of it, on the broader concepts, you know, whatever people want. So that's my opening remarks.
Oh, good. Can you hear me now?
Yeah.
Well, I have a whole bunch of questions. I read Marcia Freeman's article in the 1990 21st Century about mining the moon. And the first thing I would like it if you could just show what the chemical reactions are of deuterium, tritium, how that works, what comes off, and then helium-3 and deuterium, I guess is what it is. And then also, if you could explain more how this plasma works with the charged particles to generate electricity directly, so we can avoid all these steps of the turbines and the steam. That would be interesting. And then I also am really curious about the surface of the moon and this peculiar dirt that seems to stick to everything, and the problems posed by what you have to do to actually mine this to get the helium-3. But that's another. Anyway, that's a lot to start with, and other people probably have questions.
Okay. I will Start with the first question. So you should be able to see this little chart here that I think Natalie actually drew this out and illustrated this for us. But here is an illustration of 4 different types of fusion reactions. At the top, you have the fusion of 2 types of hydrogen, deuterium and tritium. And you can see that each of those elements is made of the red particles, which are neutrons, which are neutral, which means they don't have a charge and they're not susceptible to magnetic fields or electrical fields. And they have the little green component with the plus, which is the proton. And protons are positively charged, so they can be controlled by a magnetic field. So when you have a plasma, you have these nuclei floating around, so to speak. And if you can get them to come together with enough energy, you can get them to fuse. And that arrow pointing to the right is what happens after a fusion process between a deuterium and a tritium nuclei. You have transmutation, you have the creation of a new element, the transformation of hydrogen into helium, a different element, and the release of a free and extra neutron, this uncharged particle, which then flies right out of the plasma because it has no charge, so it cannot be controlled by a magnetic field. And on the far right, you have a measure of the amount of energy released. You have a lot of energy given the size of these particles, a huge amount of energy being released relative to the mass of these things. So that's a kind of basic deuterium-tritium reaction. That's basically the first generation fuel that a lot of fusion scientists had been hoping for and working towards under the initial stages of various fusion programs. Right below that, you see you could fuse 2 deuterium atoms. Instead of a deuterium and a tritium, you can fuse 2 deuteriums, and that can give you one of 2 options. Sometimes you'll create a helium with a neutron. Other times you'll create a hydrogen with a tritium. And I believe it's about 50-50 for which are created. But as you can see, each of those reactions releases significantly less energy than the deuterium-tritium reaction. And I believe it actually requires a fair amount more temperature to get that reaction to occur. And but then below that, so those are your variations of hydrogen fuels. And the bottom 2 are, as I described, two reactions with helium-3, helium-3 fuels, which is this special isotope, the special type of helium. And the first one is fusing 2 helium atoms, and you get out of that a helium-4 and 2 hydrogens. And below that is a deuterium helium-3 reaction, which gives you, again, a hydrogen or a proton and a helium-4. So people can take the time and look at this. If it's not clear, if these are just words that people are not familiar with, they can sit down and look through and kind of study these reactions a little more closely. But again, the point is with the bottom 2 reactions, you get results where everything has a little plus to it, meaning everything has a charge, meaning you can contain everything created by the fusion reaction in the plasma. You will get a little side effect that's you'll get some neutrons as a side effect, but that can be significantly minimized to the point where it's not really much of a problem at all. But the point is, there's various types of fuels that can give you this result where all the products, everything created, are charged particles, and it's maintained in the plasma. But the fuel that does it at the lowest temperature, the most accessible advanced fuel, is deuterium helium-3. That's the fusion reaction which has the lowest temperature required to initiate and sustain the fusion process to provide power, where everything involved, all the products resulting from it, are charged particles. So it's like the optimal entry beginning of the development of an advanced fusion economy. To look at your second question here's an illustration might be help to. There would be. I could find some better graphics and videos that kind of illustrate this a little bit more clearly. Here's the inside of a tokamak, where there's obviously two pictures here that are mixed together. The one on the right showing what it looks like when a fusion plasma is being created inside of a fusion reactor. So it's pretty interesting looking. Any type of matter, as we're familiar with, has various states. You have water. Water can be a liquid. Water can be a solid when it's frozen, and water can be a gas. But any form of matter also has an additional state called a plasma, which is when you bring it up to a high enough temperature, the electrons which orbit the atoms, which are part of the every atom in the material, begin to separate apart. You lose the balance of charges in each element of the material, and you enter a new state where the electrons, I don't really have a picture of an atom here, but the electrons which had surrounded the atom are now free and loose in this larger state, and you get a completely new state of matter called a plasma. And plasmas have very different characteristics than gases, and you can do a lot of things by controlling these plasmas with magnetic fields and electrical fields, and you can create you can induce the plasmas to create certain structures by various methods of confinement and tricks and various things. But the point is, it's an entire new state of matter you're dealing with, and fusion occurs at tens of millions of degrees, or hundreds of millions of degrees. I mean, these numbers are, more or less meaningless to most of us. It's just a giant number. These temperatures can be significantly hotter than anything we know about the sun, for example. So you can have, so to get fusion to occur, it requires incredibly high temperatures. So you can't contain that. You couldn't do that in your internal combustion engine in your car, right? You couldn't have no material we have can hold something that hot. Metal, ceramics, anything. Nothing is going to hold something that's hundreds of millions of degrees and not be torn apart by it. So what we have to do is we have to use, under one of the main methods of developing fusion, we have to use magnetic fields, very strong magnets, to kind of create a magnetic bubble, so to speak, that keeps the plasma in a certain shape, in a certain configuration. It keeps the plasma from touching the walls of the reactor and keeps it kind of floating in the middle space of this fusion reactor system you're dealing with. So that's the basic concept you're dealing with there. And then on the lunar soil, I would direct you. Natalie has a very good article that's on the China Helium-3 page of the LaRouche PAC website, which goes through in greater detail than I'd be able to do off the top of my head here, in exactly how these helium-3 particles become embedded within and contained within the lunar soil. The lunar regolith is the technical term, and how that process has built up this store of helium-3 over a long period of time. And what's been studied and demonstrated with samples of the moon brought back is that if you take the fine powder on the surface of the moon and you heat it up to, not incredibly hot temperatures, even a few hundred degrees, like 600-800 degrees, something to that effect, you can actually begin to release these gases. And then you have various other methods, which are again not things we don't know how to do, of trapping those gases and then separating them and condensing them. These are all things that we do on Earth, that we've been able to do on Earth. It'll obviously be a challenge doing it on the moon, a new planetary body. But the basic methods involved are not things that are just some crazy pie-in-the-sky idea that someone thought up and no one's ever demonstrated. I mean, these are types of processing that are within reach. What would be required would be the level of investment to really build up this whole infrastructure, space transportation, this whole development of the moon. Build up permanent bases on the moon, build up the mining equipment, the transportation equipment. So there has to be a major investment put up front. But that's going to revolutionize mankind's existence on Earth and our access to the solar system. That will also make the moon the stepping stone to the entire solar system. It will allow us to utilize our to potentially begin larger scale constructions on the moon, to begin using helium-3 fuel from the moon as a transportation fuel to travel around the whole solar system. It's really, the investment will pay off many fold, because it's literally bringing mankind to a new stage in the development of mankind's relationship to the universe as a whole.
You didn't talk about how the charged plasma is directly converted to electricity.
Yeah, there's many things on that. I'm actually not an expert on all the different aspects, but there's various ways. You can do it using, so you're dealing with this plasma. You have a relationship where moving magnetic fields will generate electricity. That's literally how all of our turbines work. If you have a dam, a hydroelectric dam, the water coming down is spinning a turbine, which is turning magnets within a magnetic field and inducing the generation of electricity. You can actually do something similar in one method in the plasma itself. You can kind of compress and expand the magnetic field, magnetic characteristics of the plasma, and literally induce an electrical current in certain electrical systems surrounding the system. So you can use the direct magnetic effects of the plasma to induce an electrical current directly from the plasma itself. So that's instead of going from a fusion reaction to generating a neutron, which heats up water, which turns into steam, which turns a turbine, which then spins a magnetic field in a magnet to generate electricity. You're going right to the properties of the plasma itself and utilizing the magnetic properties of the plasma to potentially induce a current. That's one way of doing it. There's another way using the electrostatic properties, which I'm actually not as familiar with. We could do a little bit more work on clarifying and elaborating that method. But again, you're dealing with this electrical and magnetic properties of the plasma itself, and you're able to generate the electricity directly from that. Another method that's been investigated by some of the people who are looking at helium-3 fuel specifically is that under certain conditions, the fusion plasma actually can emit radiation. And if you do it in the right way, you can induce the plasma to emit microwaves. So you're kind of structuring the plasma so it releases its energy in the form of microwaves. And then you can use systems that can actually capture those microwaves and convert them into electricity directly. So it's another method of direct conversion. And that could theoretically get up to something like 80 to 90%. You know, maybe in a practical application, it might be more like 70 to 80%. There's a lot of studies and a lot of investigations and different experiments that have been done. I'm certainly not an expert on everything that's been done, but certainly in that range, you can get 70 to 80% efficiency of converting the energy of your fusion reactions. If you induce the plasma to emit these microwaves, and then you're converting these microwaves to electricity with these things they call rectennas. So that's a third method. So there's various other there's various methods that have been studied and investigated. You know, some people that Lawrence Livermore in the national labs, they've done studies on this, and there's many papers and proposals for how these systems could work. But it's kind of, I think it's interesting to look at it as a whole new class of activity. You know, as I said, all power generation up until this point has been based upon the steam cycle and turbine cycles to generate electricity in that method. Variations of that basic concept. Now we're looking at a whole kind of new class of activity where we're working directly with the properties of the plasma to get more efficient methods of converting the one type of energy into another type of energy, converting the fusion energy, the plasma energy into electricity. And really that's part of a broader spectrum of activity where we could use the plasma itself to break down any material and to pull out resources we want out of that material. You know, there's been designs for what they call the fusion torch, where you would utilize a very high temperature plasma, potentially a fusion plasma, and then basically whatever material you could put into that, you could instantly vaporize and break apart to all its constituent elements, and then you could separate those elements out. So I'm certainly not saying this is something we could begin to do soon. You know, it might be a little bit further down the line, but at a certain point, with a really advanced economy, it's conceivable that we could go to landfills filled with trash. You know, what is trash? Trash includes elements we use. It's just not in a form or quality that we want to use them anymore. But landfills are packed with all the materials that humans need for human society. You know, it's all stuff we utilize. That's why we create it as a landfill. You know, it's conceivable that at a certain point we could certainly mine these things as as resource deposits. You know, with a very high temperature fusion plasma or plasma processing system, you could utilize the extreme high temperatures of the plasma that literally break apart all the individual atoms of whatever material you put in there, and then separate them out as pure elements, as resources. There's other investigations of how you can induce plasmas to emit other frequencies of light, frequencies of radiation, which can help create new chemicals or make certain chemical processes more efficient. You get into some kind of technical details on some of this stuff, but the point is, it's kind of all part of a new domain of, you know, what the Fusion Energy Foundation and the LaRouche movement used to call directed energy, a whole domain of controlled high temperature processes and directed qualities of energy, where you're moving beyond just using heat. You're not just using bulk heat to do things. You're using the precise control of plasmas to get them to do very specific things, to emit very specific frequencies of radiation, to break down materials in a very specific way. So you're using precisely controlled qualities of these plasmas and these higher forms of higher qualities of energy for these particular qualitative characteristics, and not just raw heat per se. So there's a lot more examples that could maybe make that a little bit clearer and put more substance to that, but hopefully that suffices as a sketch to kind of give an idea that we're talking about a totally new domain of activity, a totally new class of activity that, again, will completely revolutionize our ability to access all the resources we need, that will completely upgrade and transform the productivity of our labor force, will ensure that our workers can be more and more productive with their labor, so we can support a growing society at higher living standards, higher qualities of everything you need to sustain society, with a high-skilled, high-technology labor force.
Hi, maybe this is kind of obvious, but it's the case that we already have these plasmas, but they take a huge amount of energy to create, and we're trying to figure out how to create the conditions for a self-sustaining fusion process that would be ongoing, and so we would have this plasma to play with and get electricity out of and everything else. And what are some of the theories on what we need to do to get that? I guess we're trying to copy the sun, but not really, because it's different here on Earth. But sorry.
Yeah, there's a lot that can be said. The real answer is we just have to do it. There are a number of different, many different designs of things that could be built with existing technology, which very likely could be operational, useful first-generation fusion reactors. The reason none of those exist is because fusion has been suppressed as a technology for decades. And there's a number of examples that could be gone through. I think you know, there's one outfit actually in your neck of the woods, in the New Jersey area, Lawrenceville Plasma Physics, and they certainly don't have the answer to everything, but they have one avenue towards one type of fusion power, which again will not solve everything. It's not going to be the end-all be-all, but it's part of a developing fusion economy, could be a useful aspect in the context of everything. their work was just reviewed by 3 of the top. They're a private venture because the DOE won't give them any money. The government won't give them any money to do their research. So they're doing it based upon their own ability to fund their work. Their work was just reviewed by 3 of the top fusion scientists in the United States. Multi-decade career prize scientists who spent their lives in fusion. They spent their lives studying and trying to develop fusion power. And they said this is a very good operation. They said it very likely could achieve sustained fusion power. It could very likely be successful, and they gave it very high ratings just recently, earlier this year, I believe, in their review of this work. Now, this outfit is trying to get a few $100,000 to build an upgraded machine that could demonstrate what's called break-even, the generation of more power from a fusion reaction than you put in. That would be a psychological, that would be a revolution, and would really excite and really inspire much of the world scientific community, the world population, to actually see some breakthroughs in achieving break-even. And this one outfit, you know, on the review and of some of the top fusion scientists, is looking at a few $100,000 or a few $1 million is all they need to really get a major breakthrough. And they just can't get that money. They're just not given that money. And there's other outfits that are in similar situations. You know, in Wisconsin, you have some University of Wisconsin-Madison, you have some very significant work being done on fusion reactors that could burn helium-3 successfully. You know, they might run into certain challenges along the way, but it's certainly something that could be pursued and very likely could be highly successful. And they can't get a few $1 billion to really develop their program. You know, we spend literally trillions of dollars in Iraq, in the Iraq War. You know, literally trillions. And this is not bailout money. This is, you know, this is like weapons and people, and this is like physical cost. This is a physical cost to society. Bombs, fighter planes. You know, we spend, you know, not just creating money, but spending money and actually spending the physical productive capabilities of our society. An immense amount of effort going into the Iraq War, and they won't give a few million or a few $100 million or a couple billion to potentially completely revolutionize the fusion capability, the power capabilities of mankind as a whole by developing fusion. So there have been, to give just one other example, the major big international flagship operation right now is this thing called ITER, being built in France, which is kind of, there's a lot of complaints about it because it's a very complex, very expensive operation, and it's a huge international effort to build a very large tokamak fusion reactor. You know, a donut-shaped, kind of looking like this one, but significantly bigger. And at the current rate and the funding they're getting and the complexities of dealing with many nations bringing the parts together, they probably won't be operational until, I forget the exact date, but I think they'll start in the mid-2020s or early 20s, and then a little bit after that they'll start to crank things up to the full capabilities. That exact system could have been built in the 1980s, and there are designs for a larger system, which would not just be an experimental system, it would actually put electricity, would actually produce electricity, generally referred to as a demonstration reactor or demo. So there's designs to build a demonstration reactor. It's just not being built. And that's the bottom line with a lot of this stuff. You have various types of fusion reactor systems that are designed and proposed and being worked on, but they're just not being supported. And there's actually an interesting process where there's a number of private companies that are actually doing some pretty interesting and significant work in attempting to develop their own fusion reactors that they can commercialize, where they're actually doing some pretty serious and advanced work as far as people can tell. There's an outfit in California operating on some of this. There's an outfit in Canada called General Fusion pursuing some of this. So the bottom line in all this is that there are designs of systems that are just being sat upon, in effect, that can operate in the conditions where you can generate fusion reactions and you can sustain fusion reactions and you can convert the energy you get from those fusion reactions to electricity or potentially other types of useful energy output for other purposes. But there's just there has been no top-down support to develop and build these things. Now I'm going to show just one other graphic here, just because I think it's really important to make sure this is absolutely clear. This is, I think probably many people have seen this probably a few times by now, but this is an analysis of funding of fusion based upon a very in-depth, serious 1976 study done by the U.S. government, done by what became the DOE. It wasn't the DOE then. It wasn't called the Department of Energy then, but it was the precursor to the DOE. It was what became the DOE. They did a very in-depth, serious, multi-volume, multi-year study on what it would take to make fusion power a reality. And they not only looked at the science, they looked at the engineering, all the technical aspects. It was a very serious and authoritative study. And what they provided was a roadmap, a pathway. They said, these are the resources you need to provide. These are the series of experimental systems that you need to build. And if you follow this path, including variations in different options and different directions you could go in, depending upon what's successful and what's not successful. So they're talking about testing different types of reactor designs to see which ones are the most successful. But they very serious and thorough study, and they showed that if you really put a full crash program effort into it, you gave ranging from a couple to $10 billion a year in 2012 dollars, you could get fusion power online in about 15 years. So from 1976 to 1990. And that was all based upon things that could be built, that could be developed, conceivably from the standpoint of 1976. They said if you want to take a little bit of a slower approach, you could get there by 2005. You could get fusion power online by 2005. And then they also said if there isn't a certain minimal level of funding, we might never get fusion at all. If you're asked to build a massive bridge and then you're given $100 a year to do it as a construction company, you're just never going to do it. You can't scale down development and progress to some pitiful level and expect to get anywhere. You need a certain level of funding, of commitment, of scientists involved, of training new scientists, of building the test machines, of working with them, of building the next generation systems. You need a certain amount of investment and resources to do these types of things. And the point is, as you can see in this graphic, the actual funding, the annual funding given to magnetic fusion from the 1970s to today has been an order of magnitude less than what was known as of the 1970s would be required to achieve fusion power. So when people say fusion is 50 years away, that's a statement of intention, not a statement of scientific or technological assessment. You know, the assessment by a number of experts in the fusion community is that we could have a demonstration fusion reactor online within 10 to 15 years. And that's a figure that different people have come to somewhat from independent paths of investigation. So it's a question of a choice. We can build tokamaks with the strength, with the magnetic field required to try and contain and sustain a fusion reaction. We can build other variations of fusion reactors which can attempt to sustain a fusion reaction. We might run into surprises along the way. We might run into new challenges we weren't thinking of. But if you actually have a top-down intention crash program effort to do it, these are things we can figure out and overcome.
Hey, Ben.
Mm-hmm.
Well, I want to give Montreal a chance if they have anything they want to comment on or ask first. But I've got something if not.
Okay. Hi, Pascal from Montreal. I recently saw the video with Natalie discussing the different types of new lasers developed.
Mm-hmm.
And, I was wondering about, because, well, originally the way I was thinking about fusion, the different processes of how to actually achieve a fusion reaction, were, you know, in the with the tokamak, with the plasma system, and also the inertial one with the laser. And I was wondering what you saw as the most promising system, because I think you were mostly discussing this idea of the plasma. Is there another way that could be produced, or with this new technology of the laser? How does that fit all in together? Maybe I'm just a little bit confused. Sorry.
Yeah, no, that's absolutely correct. There's what you referred to as inertial confinement, and this is being investigated, for example, at Lawrence Livermore. I'm not in a position to declare outright what the best method is. You know, there's a lot of promise in different avenues, and quite frankly, there's going to be probably different benefits to developing different types of technologies. You know, for example, some of the stuff I was describing with the plasma processing, or eventually using potentially fusion plasmas or plasmas that are generated through a fusion process to process materials. You know, that'd be something where you'd want to utilize a magnetic confinement system, or something along those lines. For power generation, yeah, there's a lot of investigation to using lasers, and using lasers to shoot in a lot of lasers all at one target, one pellet of fuel, and compress that fuel to the point where it fuses and ignites. And that's something that has been pursued in California at the Lawrence Livermore National Lab, where they have the what they call the National Ignition Facility, NIF, N-I-F. And they have, geez, what is it, either 92 or 192 lasers that, with incredible precision and timing, they're generated, they're kind of amped up in their frequency and their power, and they're all directed from different angles all into one pellet of fusion fuel, and they all hit it at roughly at hopefully, you know, the same time, and they compress it to such a density that the atoms inside start to fuse and then release their energy because they're fusing. So if you have deuterium and tritium in there, again, our hydrogen fuels, you get them to actually combine to create one new element and release an immense amount of energy in that process. So yeah, that's a whole other avenue. Russia has developed, there's other labs in the United States, other places in the United States that have investigated laser fusion. There's places in Europe where they've investigated laser fusion. Russia has done a lot of significant work investigating laser fusion, and China. China is now developing a laser fusion facility that's on the scale of the National Ignition Facility in California, this NIF system. So it's certainly a very promising and interesting avenue to pursue as well. So yeah, I admit I've been focusing more on the magnetic confinement and similar variations off of that are related to some degree. But yeah, there's this alternative path of inertial systems, which the idea being you fire these lasers, but then the energy released by the fusion reaction of the pellet of the fuel in the pellet is significantly more than the energy you put into it to get it to fuse. But I think the most important thing, so I'm not trying to poo-poo inertial laser confinement and hold up magnetic confinement as the only option. Both these things I think could potentially have very large merits. I think the main conception is that we're developing what Mr. LaRouche used to discuss as a platform of activity. We're really not looking for the one fusion reactor design that's just going to do everything. We want the whole domain of nuclear fusion reactions and controlled reactions of fusion products. For certain circumstances, you might want very small contained systems that can generate electricity for remote areas or for rural areas. For other cases, you might want very large, massive systems that generate a lot of electricity for industrial areas or something. Or you might want other systems where you don't generate electricity. You utilize the energy from the fusion reaction to have some of these directed energy or controlled energy effects. You're generating radiation from the plasma to help process certain chemical reactions or something along those lines. Or you're producing synthetic fuels or various other options. So it's a whole it's a whole domain of activity. It's like it's kind of like electricity itself. When we developed electricity, you have a lot of different motors that are used, or you have a lot of different generators. Certain types of electricity generators are useful for one purpose, others useful for another purpose. Sometimes you want a high voltage, sometimes you want a low voltage. It's a whole, certain things get used more than others, but it's a whole array of technologies which enable mankind to utilize this capability of electricity as a whole platform of activity. And I think we should think about fusion in a similar way. We're entering a new domain of this quality of action, of the energy density and the energy flux density of fusion reactions, which give us a whole new spectrum of potential applications. And we want to develop that as a spectrum. So there's going to be certainly certain cases, I think, where it's more beneficial for one avenue versus another avenue, but then in another case it might be the opposite. So yeah, inertial is interesting. It's certainly worth pursuing. It's in a certain sense, to some degree, demonstrated to be feasible, because that's how thermonuclear bombs work. If you look up on, the declassified and public information about how thermonuclear weapons work, thermonuclear explosions, you look up for the Ulam-Teller design, you see that the thermonuclear, the fusion part of a fusion explosion in a thermonuclear fusion reaction, as in a warhead, for example, is by a similar method of compressing fusion fuel by a burst of radiation onto it, which you actually generate with a fission reaction. So you generate a small fission explosion, which then directs a bunch of energy onto a fusion target and compresses that target till it fuses and releases all of its energy. So the idea with the laser fusion is you could do that with lasers, and then do it with smaller pellets. So you don't, you don't have an insane large explosion. You have a very, very small, controlled, very tiny explosion. But you just do it in a very small scale, and you do it pulsed with these laser pulses, and you could generate the energy of fusion reactions that way, and then generate the power from there.
Okay. Hey Ben. So I was thinking back to LaRouche's discussion on Saturday, and his remarkable joy and optimism about the situation. And I have two questions that go together. One is, I guess I'm thinking about the process of transformation of global economy that we're going through right now, where what Lynn is saying is that if once you get started on a Helium-3 project, then the conception of value is set for the world. The standard for value is set, and immediately that has an effect on everything else. What you went through earlier on the shutdown on the suppression of fusion really puts into relief what we're talking about. But I wanted to ask you to comment a little bit further on that, on the way that this new definition of value completely, how that'll change the strategic situation. And my second question is, well, more of a question is, what can you say further about LaRouche's emphasis on Kepler as it is related to this development with China and Helium-3 in particular, and why is he focused on that, considering this radical shift in the whole situation?
A couple of very good questions. On the first one, I would say it is this idea that the future is it's this kind of time reversal reality, that it is the future that determines the present. You know, what is the value of your actions in society? What's the value of your labor in society? If you're an iron worker, if you're a farmer, if you're just a part of an economic process, how can you actually have a real scientific conception of the value of what you do? We have all this monetarism, measure money and measure it with, quantity of goods and all these things. You can take a lot of these attempts that are made. But if you want to really get into the science of it, they all fall infinitely short. They can never actually measure the true scientific value of the activity of an individual in society. And you have to go to what Mr. LaRouche has rather uniquely developed in his science of physical economics, which is looking at the entirety of the economic process of an entire nation or of mankind as a whole. And where you have to start from is, are you increasing the power of that economy or of the human species as a whole to exist? He measures this in potential relative population density. You can define a rough metric for what level, what carrying capacity. How can mankind change the carrying capacity of a certain region of the environment or region of the planet? How many people can be sustained at what population density relative to a given land area? You can define these kind of, again, just take this simple idea. It's kind of cutting it a little bit short, but carrying capacity. You could say that the planet Earth has a certain carrying capacity for mankind at any one given state. So at the state of a wood-burning society, get relative to certain conditions of the land area, conditions of the biosphere, water availability, forest availability, these types of things, you could define a carrying capacity for the planet with respect to human beings, as with any animal species. But mankind has demonstrated the capability that we can willfully change that. We can, through the powers of the human mind, uniquely, we can change the carrying capacity of the planet for mankind through the power of scientific discoveries and the implementation via technologies and the development of our society through culture. Mankind can willfully change his relationship to the environment around him. And that is ultimately where you have to go to measure value, to measure the value of an individual's labor, for example. So if today you're an iron worker or you're a farmer and you're growing food for society, and that society is right now going from a bailout to a bail-in process and is inducing a hyperinflationary self-collapse of its entire financial system and destroying the physical means of survival of society, well, the actual value of your work is defined by the context of the society you're contributing to. You're feeding the people that are participating in the process of the self-destruction of that economy, of that nation. That is how you would scientifically define the value of your actions, because you can never take it abstracted from the context of the process as a whole. Now, if we're on a society that's vectored towards the development of permanent bases on the moon, the development of Helium-3 from the moon, for an advanced fusion economy on the moon and on Earth, enabling mankind to absolutely change his entire relationship to the planet Earth. Increase the carrying capacity of the Earth, so to speak, by probably an order of magnitude or more, while giving mankind access to the entirety of the inner solar system in a serious and quick and efficient way. If that is what society is vectored towards as the mission, then the people you're feeding with your work as a farmer is people that are contributing to that process. Or the iron you're producing as an iron worker is iron that's going towards the facilitation of the development of that process. So you literally are, if we actually adopt this as a science driver mission, and you have an alliance between an alliance that can make that happen. I mean, that's the other thing that Lynn is so excited about, is that there's an alliance on the planet that's fighting to make this happen. China is no joke. You're talking about well over 1 billion people. You're talking about a very strong cultural history of a people on this planet, the very strong cultural identity as a national, as a nation. And you see a commitment and a sustained commitment to initiate this whole new direction, break from this current transatlantic system, and go in this completely new direction. So you have the potential not just to do all these great things, but you have the strategic potential emerging for these things actually to occur. And with the alliance of the United States, with these powers, with China, Russia, and India, committed to succeeding in developing this mission of an advanced fusion economy, a lunar helium-3 economy, then that defines the value of what people are doing tomorrow. That the actual contribution of their work to society as a whole, the actual the scientifically definable effect of their actions, which will carry on after they're done working, after they've lived, after they've gone on, is defined by that process. They're actually contributing, that their work is facilitating the creation of this new higher state for society as a whole. So that literally does define, from the future goal back to the present, the value of the work of everybody participating in that process. And so I think Mr. LaRouche is, he's been he's lived an incredible life fighting for this shift, creating the fusion energy foundation. That's what this was all about. His SDI program to initiate a flank on the entire insanity of mutual and assured destruction in this Cold War towards a collaborative effort among the two superpowers in pursuit of overcoming the common challenges that threaten mankind in an attempt to create a global strategic framework vectored towards this type of progress and development. And now, throughout many other aspects of that fight and other fights that you can go on for hours discussing the history of what Helga and Lyndon LaRouche have done with their lives in fighting for this change, now we're starting to see that process beginning to really take hold in a potentially successful way, with the utter breakdown of the current system, the inescapable reality of that breakdown, and the now sustained and clear intention stated in the actions of China especially, and India increasingly, and Russia to a large degree, and especially the orientation of these nations towards each other and towards this development perspective. So again, in the context of all of this, I think it's very clinical to look at the significance of the fact that, Mr. LaRouche decided to make a one-note theme on helium-3 from the moon over the recent period, saying that, all of these things are absolutely excellent, correct, right, and now let's define it all from the standpoint of the science driver program, which will define the entire process, because it will ensure that we come to the highest possible state in the completion of, say, a generational cycle, and define the value and the contributions of everything leading up to that state, to that change. So I think that's, if you really want Lynn's thoughts, you have to ask Lynn. I mean, he's probably got much more developed and deeper thoughts involved in the whole thing, but I think that's certainly a way to look at it and begin to understand what we're potentially dealing with. All of that being fuel to motivate us to win, because as of now, we have no leadership in the United States. It's a complete vacuum, and it's a vacuum for us to step into and to take the leadership, take the role. This is not all guaranteed. It's exciting and inspirational that orientation exists as an active and serious orientation, but that means that we have a responsibility uniquely to make sure that the United States gets on board with that, and to fill this immense vacuum. You think there's a vacuum in space, a vacuum on the moon. That vacuum, the vacuum of space, pales in comparison to the vacuum of leadership in the United States right now. What we're seeing is a joke, a sad joke. And what we need is our organization and Mr. LaRouche to step forward and become that voice of leadership in cutting through all this other insanity and crap and saying, you want to live? You want a future. You want your coming generations to exist. You want them to have a better life than you had, to progress. This is what you need to do. This is where the world is going. This is where the majority of the world population is going. If you want your life to mean anything, you're going to fight to join that process. And that's on us right now. That's not on the Congress. They've already shown their colors on many of these things. You know, that's not on your local politician. It's on us to put it on them. It's on us to make it happen. So that's what we're dealing with. We're looking at. Regarding your second question, I mean, there is a lot that could be said here, and I think Mr. LaRouche probably has a deeper idea than I've kind of fully fleshed out, frankly, myself. But I could tell you my perspective on what he's saying about what you call the broader ontological implications of what we're looking at. He, I think, has got some. We were actually talking with him about it today for a little while, and he brought it up a few times. I'm still trying to get my mind fully around his conception of the connection between the great scientific revolution of Kepler, Johannes Kepler, and the connection of that, or the application of that, to the current perspective of the development of the moon and mankind's entry into the solar system. But my clearest conception is that it is a resounding demonstration of what mankind is in the universe. That what we're looking at with this advanced fusion economy, this idea of a lunar development and the entry of mankind into the inner solar system as an active force of creative development, of control, of development, and of improvement of this region of the inner solar system. You're seeing a remarkable expression and demonstration of what mankind represents as a unique creative force in the universe as a whole. Now, if you look at Kepler's work, Kepler was able to define and scientifically discover the solar system as a single process. He was able to discover that the solar system was organized as a single harmonic system, governed by a single principle of gravitation. That he showed that the processes in the universe are governed by what we call universal physical principles, principles of action, and that mankind uniquely can discover these principles. That mankind, through the powers of the human mind, absolutely distinct from any form of animal, mankind can come to discover and know the principles that govern the universe, as Kepler demonstrated to us. But then what do we have with this prospect before us of an advanced helium-3 fusion stage of mankind? You have the perspective of mankind coming to act on the scale of the principle of the solar system. You have mankind showing the potential to express itself, that whereas up to this point processes in the solar system have been governed and determined by this principle of gravitation, now you have the beginning of the potential for the emergence of a new force to become a controlling and determining force in the solar system, and that is mankind. And you have the prospect of mankind, you could say, becoming of the domain of principle in the universe. entering the domain of activity that was prior only attributed to the principle of gravitation in terms of the control of the solar system as a single bounded process. And I think you could find many expressions of this. Mr. LaRouche got very excited when, in one of our discussions, somebody made the point that mankind is, with our fusion reactions, we're actually beginning to create conditions more powerful to certain degrees than the sun. That if you compare, relative to size, obviously, relative to the size of the process, if you compare the energy flux density or the energy per time per mass per weight of a fusion system designed by mankind on Earth, and you compare that with the sun, mankind's fusion is actually orders of magnitude higher energy flux density than the sun. There's actually a more powerful, a more highly organized, a more highly controlled process. We create temperatures in these fusion systems hotter than the sun. Densities greater than the density at the core of the sun, as far as we believe we understand it. Brightnesses brighter than the sun. We can utilize the ability to kind of control this whole domain of fusion reactions to then give us access to the solar system in the large. And mankind can begin to act as a determining force in the solar system as a whole. Act as I think, it's not to introduce too many new concepts here at this point, but I think the reference to the work of Vladimir Vernadsky, I think, is crucial to understand this. And I think Vladimir Vernadsky, the great Russian scientist, would have found immense, profound implications in this era we're looking at before us now. Vernadsky defined very clearly the process of mankind becoming what he called a geological force or a planetary force. That the power of human thought was becoming and became the governing force of the planet, shaping the planet, shaping the biosphere, improving the biosphere, improving the activity of the planet, increasing the energy flux density of the whole system. And that has defined mankind's existence, and that has defined progress up to this point. Now we're at the point where you're looking at the prospect of mankind becoming not a planetary force or a geological force, but a stellar force. Literally a stellar force. Mankind operating on the scale of a stellar system, a solar system. That mankind, we're not there yet, we're not there next year, we're not there in a generation, but we're beginning to take the initial steps, which are showing expressions, undeniable, scientifically demonstrable expressions, that mankind is beginning to be able to wield the power to affect and influence processes on the scale of solar activity and of the solar system. And you can take all of this back then to the work of Kepler, because Kepler was the one who discovered and defined the solar system as a principle, as a universal physical principle of a self-bounded single process. And mankind is now beginning to rise to the level of that process that Kepler defined.
Hey Ben, this has been truly excellent. I just want to mention that probably most of us are going to have to wrap up here in the next few minutes as it's getting kind of late. But I don't see any reason why people who want to stay on couldn't stay on. But just so you know.
Okay.
I just had a a quick question. Like the atom of the helium-3, like
Mhm.
the ratio, the size of it, if you can like compare it to something to see how small it is.
Ah, that's a good question. I wish off the top of my head, I probably couldn't. It's really, really small, smaller than you could imagine. It's tiny. That's a good question. I can find some fun comparisons that will give you an idea and send them to you. I'd have to look up some stuff though to give you a clear idea. I just don't have it off the top of my head. But you can find fun animations online where you can kind of scale down and see the relative sizes of things, and you can see what scale an atom is. It's incredibly small. We're talking about, you know, in even small objects that you can hardly see. You're talking about, I don't know, billions or some huge number of atoms, and even the tiniest things you can see. So it's an incredibly small process you're dealing with, and it really is amazing that we can begin to affect and influence and control processes on this scale, on this tiny scale. It's kind of a remarkable thing in and of itself to think about the power of the human mind to create apparatuses and structures and understand what's happening on such a tiny scale. And we don't understand a lot of it. I discussed these terms, particles, the neutron particle, the electron particles. We don't know what the hell's going on down there, really. I mean, there's certain characteristics that we kind of describe in terms of processes we're familiar with. But then there's other expressions that completely violate and are completely unexplainable in terms of anything we know about the macroscopic, experience you experience with your senses. So, there's things going on down there that we can affect, that we know how they respond, we can control them, we can do certain things. But there's absolutely going to be a lot more to figure out, and it's going to be a very interesting process to figure out what new discoveries on this domain will enable mankind to do in expanding mankind's capabilities. But just the idea that we can control processes on the very small to that degree, and the fact that the control of reactions in the infinitesimally small with these fusion reactions enables us to control processes on the largest scale of the planet, of the solar system, of the Earth and the Moon system, of the inner solar system to start, is a very provocative conception. And again, I think we're kind of working more in this direction to look at this a little bit more rigorously and thoroughly from the eyes of Vernadsky, and look at the implications, so to speak, of this new domain of activity that mankind is moving into. So we'll have a lot more coming that can kind of flesh out various aspects of this. But I can send you some stuff, Ray, to kind of give you some fun ideas. You really need some good comparisons to get a sense of these things.
I have a quick question about Mars.
Mm-hmm.
Mars used to have an atmosphere, but currently it's very thin, and it currently doesn't have a magnetic field, although it may have in the past. So I'm just wondering whether anyone has speculated about whether helium-3 might have accumulated to any degree on Mars.
That's a good question. I would have to look into that. I'm not totally sure. That's a very good question. Also, Venus has no magnetic field, though it has an atmosphere, and I don't know all the details about how helium would interact with the atmosphere. And there's also the question of asteroids, which are also exposed to the solar wind at all times. So they might also carry deposits of it. That's a good question. I just don't know the answer. I have to look into it a little bit. I'm sure there's some of it's available. I'm sure some people have some idea. I don't know if we have any direct answers or not. Perhaps our friend up there, Curiosity, could help answer some questions if they haven't been answered yet. But the process of Mars is certainly a very interesting one, and why it lost its magnetic field, what that did to the atmosphere, what that did to water, fresh water, liquid water, which almost certainly existed across much of the Martian surface earlier on in its history. And then, since the loss of these things, the loss of the atmosphere, the loss of its magnetic field, did it accumulate significant amounts of helium-3? Yeah, that's certainly a very good question. The other place that people have said we can look and go to is the gas giants. Jupiter, Saturn, Uranus, Neptune, that they actually, it's believed, contain significant amounts of helium-3 themselves. Although it's obviously more difficult to get out there, but if we had 4 generations, if we had 3 or 4 generations under a serious driver program of developing the moon and utilizing the helium-3 resources on the moon, we could be all over this. We could be all over this solar system, and we could be accessing all these other deposits of this stuff. I think there's no question about that. But it's all going to be enabled by this initial step, the development of the moon. That's our kind of our stepping stone, so to speak. I think Leona was referring to a quote of Kraft Erica, where Kraft Erica said, if God had intended mankind to leave the planet and visit the and enter the solar system and develop the solar system, he would have given mankind a moon. So we see what God intended, and we see what we have here. So that's going to be our entry point into all these things.
Yeah, Ben.
Mm-hmm.
I wanted to ask something maybe more technical about mining the moon, and what we actually know about the nature of the regolith. We've only had 2 weeks of experience on the moon with the astronauts who went there.
Yeah.
They had machines like the rover, but do we have any way of knowing what machinery would actually do under those circumstances? And
what affects the
moon dust?
What effects would have to be dealt with in operating on the moon? Yeah. There's certainly a lot of concern and interest and investigation into this. Natalie has done a lot more work than I have, so I would defer to her, and there's other studies we can look at that have treated this question in greater detail. We know a lot about it because a lot of it was brought back by the Apollo astronauts. We've been able to study a lot of the properties of it in labs all over the United States and all over the world. So we certainly have a decent working understanding of what the material is we're dealing with up there. And in regards to operating on the moon itself, it's been noted that this incredibly fine regolith, this incredibly fine dust that covers the whole moon, for these astronauts, it got everywhere. It got all over their suits. It got inside of their suits. It got inside of the door hinges it just leaked in everywhere. It was corrosive. It's very kind of jagged and sharp, so it would wear down material. So there's certainly going to be some challenges involved. in figuring some of this stuff out. There's there's been potentially certain electrostatic or magnetic fields could potentially be used to kind of keep some of it away. We certainly might have to develop some new processes to deal with this type of stuff. And I'm sure that people have been looking at this in significant detail, because the difficulties in dealing with the material for the Apollo astronauts are well known. And one of the leading proponents in the United States of mining helium-3 from the moon and bringing it back to the Earth personally dealt with these challenges. Harrison Schmitt, he was part of the last Apollo mission, and he was on the lunar surface. He was dealt with this stuff. He brought some of it back as part of all these operations that brought it back. He studied it, and he's become one of the leading proponents in the United States of returning to the moon to mine helium-3 and bring it back to the Earth. And he's even put out certain estimates that he has done in collaboration with some other people that are looking at the range of $50 billion and 15 years as a potential time frame and cost to begin a process of bringing some of this stuff back in the development of a whole lunar mining export operation. I don't know if he's got everything figured out down to every detail, and I'm sure there's going to be more work to be done, and we certainly want to look very closely at what China's planning and what the Russians have looked at in their plans to do very similar things. But yeah, we'll have to look into that and see a little bit more closely exactly how much of a concern these guys think it would be, and to the degree there's concerns there, what they think about how they're going to deal with it, because it's certainly not something that they're unaware of, and it could just be the case that for larger machinery type systems, built out of solid metals and different things, it might not be as big of a deal as it is for like the corrosive effects on a human suit or something. But anyway, I'm sure there's a lot more to look at into that. Natalie might just know off the top of her head a lot of these answers, but that's as much as I could say right now.
Thank you, Sensei.
Yeah, thanks a lot. We have to jump off now.
Okay.
Goodbye from Montreal.
All right. Anything else from New Jersey?
I don't think so.
Okay.
Thanks a lot.
Yep.
Guys, we'll be in touch.
Good. Yes.